Hello.
Hello, good morning everyone. Hello, hello, hello. Hello, hello. Yeah. Good morning, everyone. So you can continue discussion after a short talk. And this is the last talk that we do have. So far, it's amazing having a conversation with you guys. It's always kind of like very interesting. So today's topic is principles and examples of biosensor operation. So I think this is very basic topic because most of the things you may know. You may know about the principles and you may know about some examples of biosensor. So let's go through this one and we will discuss whatever the question we do have. So this is the outline of today's presentation. So first we discuss about key characteristic of biosensor, then a short discussion about classification of biosensor, and then method of immobilization, and finally we will go to principles of detection, and then there are different principles for detection. So few out of them is like piezoelectric biosensor, second is electrochemical biosensor, and optical biosensor. For each technique, we will have one or two examples to demonstrate how really they work. So the definition of biosensor. If you see the definition of biosensor few years back, the definition was not same whatever we do have now. So the biosensor is a device that measures biological or chemical reactions by generating signal proportional to the concentration of an analyte in the reaction. And this is one example here. So this all component they should be part of the biosensor. So first is analyte. So and in analyte means what you want to detect. And after biorecognitions, we do have this transducer. So transducer will detect and transfer the signal to the electronics. And then you will have signal processing to your display. So this is a simple flow chart how a biosensor works. A little bit history about biosensor. So the first biosensor was in 1906 on glass electrode, and then 1922, that is pH glass electrode. So that was the first biosensor. And then in 1962, that is first enzyme electrode for glucose detection. 1969, first potentiometric biosensor. And then 1972, it's piezoelectric biosensor. 1985, ECL immunoassay. And then here, that's a 1991, that's about this red blood cell. That's a foundation for PEC biosensing. And then going on. So in 2008, we have mobile phone assisted sensing, and 2019, electronic biosensor tattoo, and that's a 3-channel sensing here. Here in 2020, we have advanced signal processing and point of care application, and currently we are in the domain we designing multifunctional wearable and implantable sensing devices. So this is kind of like a flowchart or progress we do have made in the field of biosensing. So starting from a simple one and coming to the multifunctional, wearable and implantable sensing device, almost 100 years progress it is. The characteristic of a biosensor, so it looks like pretty simple device, and you can say just, like you put your blood and you can detect the glucose. But it's not so straightforward. There are many, many characteristics that we need to be careful when we make a device. First is your sensor should be specific to any analyte, whatever you want to detect. Then second is sensitive within biological range. So here biological range is that is found, like for example, in blood or in any sample. So sensors should be able to detect concentration within that specific range. And then it should be stable for several months, able to be used 5,000 to 10,000 times, though I do not agree with this point because we need to design sensor either use and throw or reusable. If that's a reusable, then definitely that's great. But if you wanna design the sensor like strip a tiny transducer for use and throw, then simply one time you use and then throw it. And shelf life, that's very, very important. Should be at least 6 months. It means your sensor should be stable up to 6 months without degradation in the performance or the quality. And here, capable of miniaturization. Fast response, that's definitely very, very important here. And this is the primary condition. It should not be poisonous. And here are a couple of points like sensitivity, low detection limit, cost, simplicity, speed, accuracy. So these are the points that we need to care of when we develop or design a sensing device. So all these components must be considered. And here some more components like reproducibility, ease of calibration, stability. So all these things should be considered when you go for a final biosensing product. If you are doing some research and just say your sensor is very sensitive, that's okay, that's a good point. But that's not for final production, right? Here are a couple of things about biosensor characteristic. One is linearity. So linearity means here the calibration graph should have a linear from lower concentration to higher concentration. So linearity of the sensor must be high for detection of high substrate concentration. You see here one example. So here we have a concentration from 0.1 millimole to, for example, 20 millimole. But within this domain, we have two lines. One is the straight line here, second is the straight line here. So this sensor is not a good example because it doesn't follow linearity in a wide range. So for a good sensor, it should possess the linearity in a wide range. The second is sensitivity. So definitely means the sensor should be able to detect very low concentration. So for example, here in this case, we can have a signal for 10 micromole. So that's a pretty good sensitivity here. Couple of more selectivity. So because these biomolecules, they have so many other molecules, and the biosensor should be very specific for particular one. Like for example, blood. So blood has so many components, right? It's not just only one particular type of compound there. So your sensor should be very specific to the targeted compound. So for example here, for glucose sensing, these are different dopamine or uric acid. So you see here it will have a very tiny signal, but it's very sensitive to glucose. Response time, the necessary time for obtaining 95% of the response. So it should have a very short response time as well. So these are the primary characteristics for a biosensor. The classification of biosensor. Yesterday, I think Savita, she discussed about this one, right, in the lab. She showed you that means initially biosensor can be classified based on generation, first, second, third, fourth. It's a very simple understanding. Every time we go from one step forward, we are removing one component. We are eliminating one component from its device. For example, in first case, you have these FAD to FADH2. Here also you have FAD to FADH2. You have glucose to gluconic acid, same you have here. But this you don't have, means conversion of H2O to O2. Here you don't have H2O to conversion here. In second case, now simply means you are eliminating this mediator. Here, when you go to second step to third step, mediator is eliminated. And when you go from third step to fourth step, this enzyme, they are also eliminated. So it's a very straightforward. Simply you are simplifying your glucose sensing device. As less component you will have, the better you can get. It's a very basic thing. But that was a simple classification. These biosensors can be classified in different way as well. So there are a couple of ways. First is based on bioreceptor, and the second is based on transducer. So based on bioreceptor, you can classify these biosensors like antibody, enzyme, or aptamer sensor. And based on transducer, you can categorize, for example, electrochemical. And then when you talk about electrochemical, there are some subcategories. Like here, you will have amperometric, potentiometric, voltammetric, or impedometric. Then you will have optical. So again, there are some subcategories like optical fiber and chromogenic here. And then you have gravimetric. Here you talk about piezoelectric and magnetoelastic. And there are some other categories too. So based on how transducer work, you can categorize or classify your biosensor. So there are two simple classifications. When we talk about the biosensor, so except four categories, fourth generation, first, second, and third, for all three generation biosensor, we need some enzyme to be immobilized. And there are three different ways. Either you can entrap or encapsulate, or you can do a covalent binding, or you can have a cross-linking, or number four, simply you can mix it. So there are four different ways to immobilize this enzyme into your electrode for glucose sensing application. And each method has their advantage and disadvantage. For example, the first one, that is a very gentle treatment, and there is no direct chemical modification. And this is, like a specific for catalyst and analyte interaction remains. So it's very specific, means the basic characteristic remain of that enzyme. In this case, when we have covalent bonding, so here we have a strong binding force between biocatalyst and matrix. So when we have a strong force, so it will not come out from the surface easily. Means stability will remain better here. And when we have cross-linking, so here used in conjunction with entrapment to reduce loss of biocomponent activity. So these are couple advantages, and for each technique, we have multiple kind of like disadvantage here. For example, cross-linking, harsh treatment with toxic chemical, and covalent linkage formed among us protein molecules rather than matrix. That can happen. So you have to be very careful which method you want to choose. Again, for the basic research, you can pick up anyone depending on your research interest. But for final application, you have to be very careful. So the topic of the talk today is providing the basic principle of detection with some example. So there are four different categories. One is piezoelectric here. So in this case, we measure change in the mass. The second is electrochemical. We measure the change in electrical current and potential. Then we have optical. So we measure change in light intensity. And then last one is calorimetric, and we measure change here in the heat. So these are the basic principles to design or to develop these biological sensors. So let's discuss one by one. Piezoelectric biosensor. So what is piezoelectric material? Or what is piezoelectric biosensor? So they are a group of analytical device working on a principle of affinity interaction recording. And you need to have a simple piezoelectric waveform like a piezoelectric crystal. And the principle is here: the change in the oscillation due to mass bound on the piezoelectric crystal surface. So simply you are observing change in the oscillation, and then that oscillation can be converted to, for example, mass, or for example, the concentration that you do have. And here you should know that means the change in frequency that is proportional to the mass of absorbed material. Anybody know means what is the relation between oscillation frequency and the mass? Any thought? When we have this piezoelectric device, what is the relation between frequency and mass? So for sensing application, there is a very simple relation. That is delta M equal to minus C multiplied delta F divided by N. Especially that is for QCM here. So the relationship between crystal resonance frequency and its mass, that is found out in 1959 by Sobre, and the equation name, the name of this equation is Sobre equation. And he discovered this one when he was a PhD student. So that was a great work by that student here. So the formula is here: delta n equal to minus C multiplied delta F divided by N. Here the resonance frequency change, that is delta F, change in the mass, that is delta M, and C is a sensitivity constant here. And it is related to the properties of the quartz. Here is a simple demonstration of piezoelectric biosensor. So simply, initially you will have this piezoelectric sensor, and then some biomolecule will come, absorb on the surface. So you will see change in the height, simultaneously you will see change in the mass. So you can detect based on the frequency how much change in mass do you have. And based on the change in the mass, you can have the concentration of analyte into the solution or wherever you want to measure it. This is one example here. So, for example here, you have on the surface either antigen or antibody. So, in this case, you are determining antigen, and so you should have antibody here, and then antigen will come, and then you will change. It will change the weight of your crystal. In opposite, you can determine the antibody. Again, it's a simple interlock reaction. A interact with the B, or B interact with the A. So that can happen. And in high frequency, they have simple like this, but in low frequency of oscillation, that will happen. This is a simple example of commercially available quartz crystal microbalance sensor with a silver electrode. And here you can see the size, the scale is in millimeters. So this is one example about piezoelectric biosensor. What about electrochemical biosensor? That's the big category. Means a lot of work has been done for electrochemical biosensor. And here, the electrochemical biosensor is the device, the analytical device that transduces biochemical event into electrical signal. And the electrical signal may be your current, resistance, impedance, or voltage. It can be anything, or a combination of two. So, for example, for impedance, It's a combination of few components here. So there are different type of electrochemical sensor: potentiometric biosensor, voltammetric biosensor, and conductometric biosensor. In this case, you have three different categories. For example, amperometry, cyclic voltammetry, linear sweep voltammetry. So today at least we will discuss 1, 2, 3, these three examples here. And here you can see corresponding graph. For example, cyclic voltammetry, simply you are sweeping the potential and recording the current. In the linear sweep voltammetry, its potential just sweep from A to B. It doesn't come back B to A. So, for example, you can sweep the potential from 0 to 1 volt, but you will not stand back 1 to 0 volt. You will stand only one side, either forward or backward. That's why it is called linear sweep voltammetry. So these are the kind of like basic category of electrochemical biosensor. So before we go to biosensor, how do we do experiment? So for the experiment, we need one electrochemical cell and we need a electrode. This is a very standard setup that you can have in your lab. Or if you don't have in your lab, you can make yourself. You can put just 3 electrodes in a beaker and then it will work. There is no problem. There is no, like we don't need vacuum, we don't need sealing of the container. Simply just put 3 electrodes and you are ready to go for biosensing application. Here, but with the time, we miniaturize the electrode. In this small screen printed electrode, we have all 3 components. Yesterday you saw that one in the lab, right? It has counter electrode, it has a working electrode, and it has a reference electrode. So it's very, very small. And there are many examples that you can print these electrodes on flexible substrate. And when we print this one on flexible substrate, so you can use for example, you can stick on the skin as a tattoo, or you can use for multiple purposes. And these tiny electrodes, they can be in different way, different shape. Like for example, you see here A, B, C. So they have a different shape or different domain here. So depending on application, you can pick up whatever you want to do. So the first category that we say amperometry. So in amperometry, what do? We keep the potential constant here. So only one potential, and just we run the experiment and record the signal with respect to the time. We record the signal with respect to the time. So it is a current versus time. So for example here, that is the current, this is the time, and here for this particular experiment, the potential was 0.4 volt. So at 0.4 volt, simply we are having this current, and when we inject glucose at any point, so simply we see change in the current. That's how we do amperometry experiment. Here is another example, same way. This is also amperometry experiment. So you have on Y scale current density and on X scale your time, and you keep your potential constant. For the sensing, there is one very important thing here. You see on the Y scale, that is a current density. So whenever you record your data, especially for the research, it should be normalized either with the surface or with the active surface area. It should be like a milliampere per centimeter square, either electrochemically active surface area or with normal standard surface area. So here in amperometry, current is measured at a constant potential, and that is referred to amperometry. What about the voltammetry? So there is a tiny difference in amperometry and voltammetry. A very tiny difference. Here in voltammetry, you will measure the current during controlled variation of the potential. So simply you are changing the potential in a controlled way and recording the current. That's what you are saying, right? So here, for example, simply you sweep the potential and record the current. And here are a couple of things that you need to be careful, like what will be the effect of the scan rate. For example, here the scan rate is 100 millivolt per second. What will happen if the scan rate is 1 millivolt per second? Or what will happen if the scan rate is 500 millivolt per second? So depends what you are looking for. Sometimes to find the kinetics of the reaction, you should have a lower scan rate. So in lower scan rate, you will not miss any activity or any reaction. Like if there is any tiny oxidation reduction is happening and the scan rate is low, so you can find it out. But with higher scan rate, those side reactions, they can be eliminated here. This is a simple example here, like you have A, B, C, D. So here simply you add the glucose and you increase the current here. This is simple one, like 100 millivolt per second scan rate. Here this is another example of flat gold and nano structure gold. So simply you can see flat gold look like very simple. But here in nano structure gold, you see how the graph look like. It going from this side to this side, and then coming back, going up, and coming back. So this is the cyclic voltammetry that will provide what's going on in the system. What type of reaction is happening at what stage. So for any type of sensing application, when you do electrochemical sensing application, it's always suggested that do very careful cyclic voltammetry experiment. Here there are just a couple of examples. First is effect of concentration. So simply when you enhance the concentration, you can see enhancement in the current density here or current. So simply means 0 to 500, so that the current is increasing at this point, going up. And same way, during this side, it's coming down. So here the question is, which region is oxidation and which one is reduction, am I right? That's one thing very simple. If you have a simple graph like this, so anybody can say, even a kid tell you that this part is oxidation, this is reduction, am I right? But this is not always the case. You don't have always a simple a graph like this. Sometimes you may have a very complicated graph too. Here, this is about the scan rate. You can see simply, when you increase the scan rate, the current is increasing in negative and on the positive side too. So higher the scan rate, higher the current. And it's a very basic rule. Because when you have the higher scan rate, so simply you are increasing the kinetic of the reaction there. And that's why you have the higher current there. As I mentioned you guys, it's not always simple to study a cyclic voltammetry graph. You see here. So this is the negative region. So when it is in negative region, anybody can say just only reduction reaction is happening. There is no oxidation, right? But here, it's oxidation is happening. There is no reduction. Oxidation is happening here. See here, first case. On cathode, that's a current. CuOOH plus 1 electron plus H2O, then you have CuOH2 plus OH minus. But in presence of glucose, the CuOOH plus glucose, it makes CuOH2 plus glucose electron and plus 1 electron. So it gives 1 electron extra. And that's the reason here. The current, when you move from low concentration to high concentration, current is decreasing, current is going up. So when you add the glucose, it's just decreasing the current. So that's why just blindly don't say that if it is downside, it's a reduction. It's not an oxidation. It's always a relative reaction. Relative to what? That's you need to understand. So that's a very basic thing about voltammetry. The third one, electrochemical biosensor based on impedance spectroscopy. When you study this electrochemistry, believe me, Try to understand impedance spectroscopy and you will get more and more confusion. It's very, very complicated, is the first thing. And if you go for mathematical modeling, then just you need to spend kind of like a month to understand the sound modeling. But in a simple way, in a very, very simple way, then you have an ideal case, a ideal impedance spectroscopy graph. So for example here, that's the same circle here. So this is a corresponding rental circuit here. So when impedance starts, so how far it is from zero in high frequency range. From here it will end at say not start. So that point will give you solution resistance, and then the second is the gap from here to here. That is your RCT, charge transfer coefficient, or charge transfer resistance. So these two parameters, they are very interesting for any electrochemical reaction. The first is what is the solution resistance. The second is charge transfer resistance. So if you have a smaller charge transfer, it means the charge transfer between electrode and analyte is happening faster. There is a small resistance for that particular component. And that's in that way, this impedance spectroscopy has been used for biosensing application. And this is a very simple application, what I'm telling you guys. It can be like this and then go a straight line. So that will be a combination of diffusion and kinetic. And then you may have here not only one, you may have 1, 2, 3 semicircle. That will be more complicated. And then you may have sometimes going up and then going down. So that will also be more complicated. So I'm telling you a very straightforward, simple example here. So in this case, like when you add the glucose, like this is your bare electrode, and then you add the glucose like 40, 100, 200, 300, 400, or 500. So the value of RCT, you see value of RCT here, is changing, it's decreasing. And the reason is that more reactant you provide, it means more reactant flows are available to the electrode. So it's easy to those reactant to the electrode. And here, based on this one, they can calculate like RCT divided by RCT0. So here then you will have a linear relationship, and based on this linear relationship, you can calculate like your limit of density or the concentration that you want to detect, or a calibration curve you can have, so you can find out an unknown concentration too. And here this is the example for this gold electrode, and that gold electrode was fabricated or functionalized with NDA molecule, and then this NDA molecule have interaction with D. So this is kind of like electrode they have used for this particular study. So that's how we can use, in a simple way, impedance spectroscopy for biological sensing applications. Next one, in previous presentation we discussed about field effect transistor, and we have seen multiple type of field effect transistor for different applications. This is one example here using a complete graphene solution gated transistor. So here we have solution gate here. So simply, and every component is graphene. That's also one important point here. All three components, your gate and here PS, all are graphene based. And for your channel, they use simple graphene, and then graphene was functionalized with PT nanoparticle, platinum nanoparticle, and then this GOX was immobilized on your channel here. So that's how they fabricated working electrode. And the beauty of that, of this work is that when you have this type of like a FET transistor, so on these EDL, the energy level that drop, and then they match with the graphene channel. Here simply you see one graph here. So that is with the PBS solution and 1 millimole glucose plus PBS solution. So simply you can see this is your PBS solution, and there is a shift in the Fermi level or in the VG here, gate voltage. And that's how this FET is sensitive for glucose. And here this FET can be used, we can measure the IBS, the current between source and drain at one particular gate voltage with varying concentration of glucose. And simply in this condition, you can see it's like a VG is 0.7 volt and VDS is 0.05 volt. So in this particular condition, when you add a glucose, so even at 0.5 volt, you can see a signal here. And then simply you can find the linear region or linearity based on the delta VC, change in the gate voltage. So this is a very, very standard or very basic application about FET, how they can be used for glucose sensing application. So far at least you understand how we can use amperometry, how we can use voltammetry, how we can use FET, and how we can use impedance spectroscopy. So these are the four basic examples for four different technologies. In this technology, we have a different way to do them, right? So these are the four basic standard applications, for example, for these four technologies. But when we talk about electrochemical biosensor, technology is very, very important, but more than technology, it's the catalyst or the electrode that you should care about. So here, despite what technology you want to use, you need to pick up the material, and there are different types of material they have been used for biological sensing application. So, for example, metal nanoparticle, in this category, then you have these for example, simple nanoparticle, then you have core cell particle, or like different structure here. Then you may have metal oxide nanoparticle, and again, this metal oxide nanoparticle, they may be different shape, or different size, or different combination of different material too. Then you can have nanocomposite hybrid, like for example, silver nanoparticle with Pani nanocomposite, or gold nanoparticle with gel nano hybrid, or gold nanoparticle and graphene hybrid. So you can create these nanocomposite or nano hybrid material. Another category definitely is a carbon nanomaterial base, and here couple of more material like 2D material like Maxine family or like PMDC family. So there are many, many catalysts that you can explore for electrochemical biosensing application. Any questions so far? Any question about amperometry, cyclic voltammetry, impedance spectroscopy? Good. The third was optical biosensor. So I thought means there may be very, like a few research in optical biosensor or the few technology for biosensing application. Today here we have Dr. Ramchandra with us. He is expert in optical material and optics. Am I right? Yes or no? Yes. Yes. So if you have any question about optics, so definitely he will be happy to help us and to discuss. So here you can see very complicated technology or method like transmission NIR spectroscopy, and here NIR is near infrared spectroscopy. And then you have diffuse reflectance NIR, transmission NIR, ATR MIR, transmission MIR, backscattered MIR, Raman spectroscopy, transmission Raman spectroscopy, surface enhanced Raman spectroscopy, fluorescence sensing, optical coherence tomography. There is something else. So here you can see means different technology they are utilized for biochemical biosensing application. And they are complicated. Means if you see transmission and IR spectroscopy, you cannot make a miniaturized instrument out for that. It's not a very simple one. Here the question I do have for you guys, Apple Watch doesn't have built-in glucose sensing so far. Any reason for that? Means Apple can give you your heart rate, right? Apple Watch can give you a lot of things, but what about like why it doesn't have a biological sensing application so far? A very simple answer is there. Huh? Can you do the math, please? To the side.
Maybe technically they can give, but in the commercial point of view, they are not interested.
So they are not interested in everyone saying, right? But I will say means they are super interested to have that technology. Because for glucose sensing, there is a one company, I think, Dexon, see something, and Apple Watch is using app for that particular device to give the sensing application, right? Anybody wanna give a clue? What may be the reason? And I know it's a couple of companies. There is one company that name is Graphwear or Graphwear. That is basically on graphene, and they have designed a watch for only glucose sensing application. And the technology is basically for graphene. A simple explanation maybe here. We don't have so far that miniaturized device for glucose sensing application, so they can fit whatever they have already in that watch. If they can have a super tiny, kind of like optical sensing device, so why do you not do that? If it is feasible. So that's one basic challenge for glucose sensing. Even despite 100 years of research, still we don't have a super tiny, kind of like a portable or super tiny device that can provide us continuous glucose sensing. We don't have that one, even after 100 years of research. We have a lot of like a tattoo, we have a lot of like a tape type of things. You can just stick on your skin. You can have a glucose sensor for your sweat or for your blood or simply like for different type of things. But we don't have a super miniaturized device that can be used for like in a compact mode. And especially when we talk about optical measurement, they are super complicated and it's very hard to miniaturize these devices here. But they have a pretty good detection limit, like here 31 milligram per liter. And there is one example, optical biosensor, fluorescence sensor. I pick up this one because this is the simplest to understand. Compared to these things, transmission, NIR, or etc., the fluorescence is the simplest kind of like a technique that you can use for sensing application here. So here, that is the basic mechanism here, the basic principle. The light will absorb and the glucose will bind and then fluorescent light will emit. So the fluorescence principle relies on the light emission from a molecule that absorbs energy at a specific wavelength from incidence radiation and is excited from the ground state to a higher energy level. That's the basic principle for fluorescence sensor. It's a very simple schematic here, and that's a tiny kind of like a device. So you see this is a sensing platform here, and here is a sensor kit, a tiny sensor kit, and then you have optical fiber, and this optical fiber will get the signal from this magnet-based optical coupler. So this is a super tiny device. It's connected here for the human body, and then it's connected to the photometer. So we need one photometer here. And when we do the analysis, so it's very precise. with your well-known glucose sensing device. So this is one example about optical biosensor, fluorescence-based optical biosensor.
What's the accuracy
It's accuracy.
sensing ability?
It's pretty fast. It's quick fast. Quick fast and accuracy you see here.
Because most of the
Yes, accuracy.
materials, some of them are more microscopic.
It is very accurate. It's super
Super
accurate.
accurate.
Yeah.
Do you have any slides for
Yeah.
Because we are expert in preparing fluorescent materials, especially platinum-based fluorescent materials. So this suppose as per your slide, if we bind the glucose,
Yeah.
then we can test it,
Yes.
and then we can go some kind of. That's why I was asking you what is the optimal level achieved so far, and what is the accuracy.
It's pretty accurate, and here it's a concentration for one particular sample, 60 milligram per day. So it's very sensitive, sir. And this is just only one example. In another research, they have detected a lower limit too.
Okay.
Yeah.
Yeah, this system is very useful actually. So for detecting, currencies and bar, they are using this kind of sensors.
Yeah. So now we are open for question and discussion. You guys can keep me today. Ask question as many as you want to have.
Sir, like for biosensor application, optical and electrochemical are the most studied one. So, but as like in the literature review, what they say is optical components are very expensive as compared with to like microelectronics. Electrochemicals and biosensors are compatible with microelectronics. So, as you showed to us, so like normally optical biosensors like it is measures the change in the intensity of the light.
Yes.
So, like as you showed, I think first time actually optical that means biosensor. So, is it cost effective comparison to electrochemical biosensors?
It's telling that depends on the material what you want to use. Again, it's like when we talk about this optical biosensor. So if you want to have this particular optical fiber, so they may be expensive. But if you want to have relatively simple setup, so I will say they may not be expensive too. Two things are expensive component there: photo detector and the optical fiber. Remaining is maybe very cheap.
So the device came into the market. So like is everyone can easily understand like the readings that glucometers are
That's-
normally that is.
That's a post-processing system, right? So you can always, whatever the data you can have, you can convert that data into a readable output. It's a technical step.
So photo detector is mandatory, like it
Yes.
has to happen.
Definitely.
Because of the light. Because there is a company for the electrochemicals, in the peak of, I think they're a European company, they say like whenever they have seminars and talks, so they always compare with optical biosensor. First thing they say is the portability so far was not possible with optical biosensor, where like rapid and accurate detection was only possible with electrochemical biosensor. They are company, but always they are on the like the top benefit was that thing. So we until now like we also had that okay, optical biosensor appreciation is not possible. But seeing today, I think like it is possible. I see you.
Yeah, it's a pretty small device, but it's not for comparison to electrochemical sensor. It's very big.
Yes.
Because for electrochemical sensor, you don't need all these components. Simply you may need one component here that can have all things together. And then you can have the reading on your cell phone. Even if it may have the transmitter itself.
Sir, is it invasive or non-invasive? Like black is a black based as well which one?
I think it's non-invasive. But here, this is just only one example. When I was working on this table, I have seen multiple articles for fluorescence. So you can go through that one too.
Just like, which is a sense, academic research is different than applied research.
Yeah.
There are many papers on every.
No, it's to understand the concept.
Okay.
Yeah.
Fine.
Again, that animation means when I was talking about Apple Watch, so one reason is to have this mini strike device. So far in 100 years, we were not able to go to that one. Like for example, for transistor, now we are able to make a transistor with 1 nanometer, right? Even smaller than 1 nanometer at a molecular level. But in this case, we are not able to move that fast.
Sir, you have said using the impedance analyzer also we can detect sensing biomolecules.
Yeah.
So if we got maybe 3 semicycles, you said that computation, procedure will be complicated. Can you at least, if we have 2 semicycles, is there any explanation for that? For 3 semicycles or 2 semicycles like that?
For 2 semicircle, explanation is there. I have not seen for 3 semicircle, but 2 semicircle, it's I think if you go to even on like GMI instrument website or any of these boosted instrument, so they have a clear impedance spectroscopy explanation, complete mathematical explanation for 2 semicircle. Again, in terms of like mathematical explanation, it's a complicated to explain. Because there are 2, what you say that one, imaginary component there. And when you have those imaginary components, so whatever reaction is happening or whatever explanation is happening, so that's more complex.
Sir, I have a question. Actually, recently this we are seeing a lot. Actually, is it better to synthesize nanomaterials which you want to work on it, or otherwise you should purchase it? Because normally in IITs like here, IITs and all, what they're doing is they're directly purchasing the material and they're using for the device fabrication. So like we are stating in some places, we are synthesizing the nanomaterials at the lab, we are using it. So like, I don't know, because
It depends on the cost. First thing, it depends on the cost. Like when we talk about this buying material, right? If they are cheap, so you can buy that one. The second is quality of the material. Because if you are synthesizing in your lab, you can control the quality the way you want, rather than means whatever you are buying. Yeah, so there's a kind of like things to be done.
I
Give the mic please to Dr. Asanja.
So one more hurdle for this is now if you buy something, if it is not authorized from the company, and what they are selling the materials, if it is not up to the mark, what we are looking for the application is not also come. That's a good way. So suppose if you have your own preparation and all, you have your own calculation and the exact measurements and the sizes and everything, you can get it. So most of the things, in case of two-dimensional organizational materials, nanobites and all, so purchasing is somewhat not giving good results. So what I heard,
Just I give you an example, means like if you want to have reduced graphene oxide. So rather than spending days and days in your lab and do all those massive work like filtration, etc., or chemical reaction, simply you can buy that one if that's a reasonable price. And because like if you synthesize reduced graphene oxide, you go for first hammer metal, right? And then you go for reduction of that material. And then during that process, there is a lot of cleaning step. And if you use hot chemical there, so one avoid that one, simply buy reduced graphene oxide because they are cheap. Yeah. Cool. Any more questions? So here today we have Dr. Ramchandra with us. He wanna share some thought for the research or how to move forward in the career for the young kids. So please, your production that come here. Yeah, yeah. With the mic, please. First, Jimmy. That's okay. Go ahead.
So very good morning to all of you. And first of all, very happy to participate in this program. And there are a lot of stories behind this young program PhD. And we would like to share some memories with you all. And I am not such a great scientist or such a great researcher, but at college level, how can we do research in an effective way? So in that zone, I explored my ideas and all. And basically, I started my career as a lecturer, and now I'm principal of one great college. It's nearly 172 years old college at government college, that is which is government college at Autonomous Trust only, and it is 172 years old of academic excellence. And there are a lot of stories with me, memories with me, with this guy and Professor Berkant, and who is the registrar of this prestigious technical university. And I'm a small researcher at college level. So in college level means basically the lecturer duty is just you know uh, to give academic excellence and to make students career prospects in a good way. That means the job is only limited to academic instruction, actually. So like the lecturer job. But nowadays, uh, so many constraints are there. So only academics is not permitted and go for some kind of research also. If that is the scenario in a small college or a degree college, how can you start a research? That's the thing actually. But when you look at Tamil Nadu, the Tamil Nadu guys are there. I had an interaction already itself. So in Tamil Nadu and all in government degree colleges also, they have very good research facilities and they are doing some good jobs and good publications. So I got motivated and then started journey, enter into a college level research actually. So for that I was selected as summer teacher fellow, so which is given by Indian Academy of Sciences. You might have noticed this. So then I got an opportunity to work with RRCAT Indore, Dr. Sunil Kumar, and he's an expert in single crystal preparations. But the single crystal preparation means there are yeah, there are many kinds of techniques are there, but basically college level research means we need small techniques. So that is solution growth single crystals. So that's what I focused initially, and then got an opportunity to have one minor research project from UGC. So this was the story in 2010 actually. So I started my laboratory with 10,000 rupees at that time, and prepared some crystals and did some characterization and published some notified journals elsewhere like that. And slowly I picked up and converted my research into nanomaterials, preparation of nanomaterials with a simple solution-based methods. Still we are using those methods, green synthesis, then co-precipitation method, polyol synthesis, and then hydrodermal method. So these techniques we adopted to prepare the nanomaterials. And slowly, I attended many meetings and then got an opportunity to work with Bharat scientist Dr. Sudarshan. And then we have, I've got a project VRNS nearly for 8 lakhs. And then I diverted my research career from single crystal solution single crystal to nano fluorescent materials, then electroluminescent materials. So as and when I finished that particular project, got an opportunity to apply to get a fellowship to go for foreign as a postdoctoral research fellow. So that means once you have G1P, so and then your age and your constraints not make you stop. So after completion of my PhD, nearly 18 years, I got an opportunity to work as a career. Then I went for abroad, met this guy, and we both, that means Professor Venkat from JNTU Hyderabad and myself at a college level, me and we went for University of Lowell call center. So they had given opportunity to work with them. And then at that time, I met this guy and then we had very good times and we worked there. But my up to that time, I had a bit experience with luminescent materials and electroluminescent materials, photoluminescent materials, and single crystal solution growth crystals. But when I moved there, then I have interacted with all the scientists. But I like most the guy who is working there. So Josh had this vision, and I interested in that. So at that time, the Josh and Vijayendra is working on CO2 conversion. So that means the CO2 conversion into a useful chemicals. So that's very challenging job actually. So that's very interesting answer. Challenging means, so we went there on Raman Fellowship. Yeah? Raman Fellowship means, you know the meaning of that means Raman Fellowship, which is provided by the government of India, and Raman has a very good, not very good, and outstanding contributions to the field of material science. And then he used to say one saying that if you have a right question, if you have a right question, and if you pose the right question, and then the nature will answer, or the nature will open her secrets. So that is the saying. So that is then when these people are working, CO2 reduction means I really don't know. So that is within 1 year, how can I complete that particular job or not? So that's the simple thing when you are looking at outside and you have a wonderful scientific reaction is going on. So that means the sunlight is falling on the green leaves and the green leaves preparing their food and giving out wonderful oxygen and consuming CO2. Is that right? So this is in general, if you look at the nature, that thing is there. But whereas if you do the same thing in laboratory, that's really exciting me actually at that time. So this guy is working on that process. That means artificial photosynthesis. I worked, but my journal is different. But where I work with them is different. But within 1 year, my challenge is to work with them and to publish at least one good paper. So at that time, I met him and then we had a very good interaction and Joe's directed us. And during that time, the Professor Venkat also came. So Professor Venkat at that time, he had an opportunity to work with Johns Hopkins University. This is the Boston, is that right? Yeah, Johns Hopkins University, that is a medical university. This is one of the world famous medical university. He had got opportunity to work with that with Sridhar sir, who's a Telugu, he's working with that, and under him he's working. So we had an opportunity during that fellowship, and you can visit other institutions also. Under that category, he came to me, and we had very fun, and he prepared some materials there, that is the reduced graphing. So reduced graphing, Venkat prepared well. There's nearly one month, 2 months he spent, and we prepared reduced graphing material and we tested it. And I also worked with reduced SN, reduced tin oxide, reduced tin oxide, I not reduced, it is pores. Nanovites.
That's a tin oxide was synthesized using a plasma technology.
Yes,
And then those tin nanowire, they were
Tin nanovites.
yeah, they were purified, so we have an porous tin nanowire.
Porous tin nanovites. So that I worked previously, then just generally preparing of nanomaterials, just like co-precipitation and polyol and hydrothermal, these kind of methods. But there I really astonished while working with them. That is what is the one part synthesis? Plasma. So that means you prepare a material and give a plasma. And the plasma, you will get the material nanomaterial formation within minutes, I guess it is. Within minutes you can get the materials. So at that time we prepared tin oxide, porous tin oxide nanovites we prepared, and we tested it for CO2 reduction. So that means CO2 reduction in the sense the artificial photosynthesis. I excited to do that kind of thing. And then the CO2 molecule has been breakdown and it has been converted into a formic acid. So useful formic acid, and we tested it, and we published that paper in a journal of materials. Yeah, journal of materials, RSA, Royal Society of Chemistry. Journal of Material Chemistry A. So nearly 11 or 12. That's the highest paper in my life. So this was the journey started with them, and then after then we had contact. And this Venkat is here, and he is. You are in now. College. A state university called Hadija. Yeah.
That is the Elizabeth City State University.
Yeah. So he worked as a professor. So, but the thing is here, why I'm sharing this story is just a college lecturer, me appointed in the government sector, and just started journey with a simple 10,000 laboratory. Now my laboratory cost is nearly 1.5 crore, and the persons who are there in our team, nearly six members are here. One research project assistant is also there, and other 5 assistant professors, one is associate professor is there, and these are all having seed money, and under that seed money they came here, and then I only the person who allotted the seed money and who encouraged the research at all. So this is the thing which I want to share. So many people over here, they are doing their PhDs and then videos, and then some of them are standard associate professors. So the sky is the only limit. You just what you do is then keep on working and get contacts, and then whatever the new things you learn, and then keep practicing. This is the only one thing what I did, and I also suggesting you to also. I also suggesting you to. So the thing is here, preparing materials and getting characterization, publishing in good journals, that particular kind of era has been gone, is what I observed in my research. So now, without any obligations, then the journals, they won't accept it. This is what I understood. So, and the AI came into the picture, and whatever you are writing and whatever you are doing, and then AI is coaching us, and then giving lot of suggestions, and then how to write and how to present our work in a best way is also a difficult thing nowadays. Whatever you write, and then somewhat somewhere your similarity, these kind of things are there. But anyway, write-up is somewhat different. That's also one so many techniques are there, so many platforms are there. So now this is what the biosensors stuff is very interesting actually. So very recently we got an electrochemical workstation under NRL funding. That is, we had in our laboratory, and we are working for some hydrogen stuff, ORR, OER, and HUR reactions, and we have now we are moving with the baby steps, and previously our staff attended a VAT one big workshop there, and this is the second one. And if you can operate accurately with the electrochemical workstation, you can do supercapacitor stuff and hydrogen stuff, and then sensors. This is three kind of things we can execute it. That's what I learned in there also. Uh, so what I suggest you, the youngsters here, and you need to work with the international level, that is competitive research. Competitive research means those who are doing PhDs. So it should be up to the mark. Then after completion of your PhD, you need to get some kind of fellowships abroad. So that means how they are doing, and all for with your results, and all for with your experimentation, all for with your ideas have to be explored. So that's what I want to tell you. So nowadays, the things are easy to go out and get the opportunities, but you need to work with the level of the things which other institutions they are following. So the basic things, almost all no use. That is basic material preparation of materials are of no use. See, uh, why we would everybody should have attention towards the biosensor and all. So there is a one area which, as per my experience, there is a one area which we can explore more and more. That is biomedical field only. So then other areas, almost all came to the saturation mode. Saturation means if you do some kind of research, that is an incremental improvement only. Incremental improvement means already existing results are there. Some kind of new techniques or new methodology or some cost-effective methods. If you choose that, that adds a somewhat incremental improvement. But whereas in biomedical field, still you need to explore. Still you need to find some kind of new biomolecules. Still you need to have some attentions on some diseases and all. So that is the reason we faced that is the whole world faced challenge to uh, face the COVID-19. Is that right? So that means still biomedical field and lot of applications are there for physicists and chemists. And in that point, this is the right time to opt this biomedical sensors and other stuff. So that's what I would like to tell you all, and very happy to interact with you all. And whatever that here many investors are there, I would like to tell you only one advice for you all. That is, whatever you have, a simple results. That's what I learned from foreign papers and foreign authors and scientists. They have very good skills actually, very good skills in writing, but where we are lagging that. So one joke is also there here, and then one friend is a research scholar and working in a good laboratory, and he went to his home, and after that he had a call from laboratory, and what you are doing? So that friend called and asked. Then I am doing here. I am doing research at my home. What kind of research you are doing? So that is hydrothermal treatment of silver, ceramic, and iron materials with non-conducive environment. So very good research you are doing. Very nice. No, no, come again. What you are doing? No, no. That is hydrothermal treatment of silver and ceramic and iron materials with non-conducive environment. Oh, that means you are doing something in the laboratory and as well as you are doing the same continuing research at home also. So the thing is what the guy said to that person who called, he just hydrothermal treatment means hot water. Hydrothermal means hot water treatment with means ions, ceramic and silver means these are the vessels. So the vessels with non-conducive environment. Non-conducive means conducive environment, positive environment. Non-conducive means unhealthy environment. Means under his wife directions, he is cleaning all the vessels with hot water. So that means how, see, how nicely he explained. That means, so once if you do in some kind of, research and all, so that means whatever you are doing and whatever you are taking or eating or that kind of sense you have in your mind. So that means how, technically he explained his, the job, what he is doing at home. So that kind of representation, technical inclusiveness has to be there while writing the papers. So that's what I want to give you the advice. And very all the best, guys. And very happy to interact with you all, and especially the Professor Vijayendra and Professor Varkar. So I had many programs at my college, very big college, nearly 230 faculty members, and then 6,500 students, and nearly 47 acres campus. That's the one and only college in the entire country who secured A plus in government sector. That's a big college. Principal had more, lot more works, but even if I want to see this particular guy and who has given a lot of motivation to carry out. And I started my laboratory at 10,000, now it is 1.5 crore worth the laboratory, and we have everything that means, and whatever some kind of what facilities I need, I have. I suppose if you have samples, we can do dielectric percent measurements, in situ dielectric percent measurements up to 1,000 degrees. Is that right, madam? Up to 800 degrees temperature, we can measure the dielectric properties and UV, FTIR, and electrochemical workstation. These are all there with us. And nearby, if any samples are there, we can do with a free of cost. It's a government institution, no money, nothing. Okay. So thank you for interacting with you all. So very nice.
Everyone, let's take a short break and meet here at 12 o'clock. Biosnesor outside.
nanoscience, Shilpa Chakra garu, and the dear participants. Very good afternoon. Indeed, happy to be a part of this validatory function on nanometers in chemicals and biosimilars. Right? So now, before going to this, I would also appreciate the GAN coordinator for taking initiative and also course coordinator, Professor Venkateshwar, who is busy and the meeting he could not attend. So he has taken a lot of time and who made this program successful. I would like to appreciate him. And also I appreciate all the participants who came all over the India for this nanomaterials. So nowadays everybody seeing already madam said. So nanomaterials is essential in almost all the engineering departments. Almost all the departments are looking towards nanoscience. I'm sure many of the participants are from different specializations. You can make use of the knowledge, whatever you might have gained from the eminent speaker. Right? So he's kind enough, I think, sparing 5 days, right? Maybe, so really you will get opportunity to come to India and in spite of the busy schedule, sir has spent 5 days here. So it's really appreciable, sir. Thank you very much for sparing your time. And I hope you might have just gone through what is the difference in approach, how we look at a problem while doing research, and how Europe and US, where they may be more focused and more industry-oriented applied research will be there. So I'm sure you got some insight into that type of research so that you can inculcate and you can follow that and so that you can add to your whatever research work which you are doing. So we will try to organize similar types of programs in this college in future also. Earlier, I think we conducted 16 programs, but after COVID, so I think this is the first program, I think. So in future also we'll try to organize. So the interested participant may come. And I will be thankful to the organizing committee for giving this opportunity. Thank you.
Now I request following faculty, Dr. Vijendra Kumar Sir, Associate Professor, Department of Technology, Elizabeth University, USA, to address on validity.
So, good afternoon, guest of honor, Dr. Biosnesor Reddy, and our chief guest, Dr. Ramabu, Dr. Ramchandra, and Dr. Shilpa Chakra, and Dr. Hemlata, and all of you. So, thank you for tolerating me 5 days, and I have a lot of fun with you guys. And I hope that you have enjoyed and you have learned about chemical sensing and nanomaterial. But my research is more beyond that one. I do a lot of work on renewable energy and a lot of work on nanocatalysts and biofuel. So if you have any interest and if you have any questions related to that, so please feel free to write email or drop a message to me. And on behalf of you, all of the students, all of the participants, I wanna thank to Haris and all team for their effort and for providing us food and for having us throughout 5 days. So thank you to all of us. And just stay happy and blessed. Thank you.
Now I request our Professor K. Venkateshwar Sir, the course coordinator, registered GNUH, to speak few words on a validatory function.
Good afternoon to one another. Before I am coming out, there is a lot of biryani, nice aroma is coming, so I don't want to take much time. So I first of all thank Dr. Vijendra, who really very supportive. I did not even felt that an international guest is there with me. I was like very reluctant. I'm very sorry. Yesterday I could take some hotel outside. Other than that, I made him to roam on the roads for Halim and biryani. So I'm very sorry, Vijendra. I could not spend much time. And I thank Ramchandra and Rambabu Garu, who is our alumni and who has his own startup, and he is uh, always very supportive. And Principal Garu, Narasimha Reddy Garu, and Shilpa Chakra, the head of the department. With her support only, you could all enjoy the department. And she is the heading the department, and you might have seen all the facilities in the department. And I wish you all the best and enjoy the lunch and certificate distribution is there. Oh, yeah. Thank you very much.
Now I request our chief guest, Dr. Atuli Rambabu sir, Director Elecon India, to address on the workshop.
Good afternoon, everyone. Hi, thank you, sir, for inviting me for this to this occasion. It's a short notice, but we managed to do it. So let me introduce myself. As said, I'm the alumni of JNU. I remember my old days that 2003. Go back to the 20 years back, almost 20 years back, 2003, where I had a chance to present on nanomaterials first time in IIT Kharagpur. So me and my friends traveled from here, with support of JNUH department. They have the numbers, trained and all these things. We traveled there and presented first time from JNUH, stating that about the zinc oxide nanoparticles. Okay, that was my first introduction to the nanomaterials field. And after that, I got interested into the topic. My background was actually what I did was here on metallurgical engineering. It's a different topic altogether. But because of my interest on the nanomaterials, I traveled to Europe. I had my master's there in nanomaterials and also PhD on the nanomaterials for different applications such as inductive applications. And afterwards, I worked for a couple of companies. Again, they are also nano-based companies. And finally, I landed in Denmark for, I was the in charge for the Danish whole country for companies who produces nanomaterials and representing in the European Union. So there, my complete journey was, let's say, professional as well as academic journey has been through the nanomaterials. Now you are having a lucky that you are having the courses here. Like I said, my journey was, we don't know about nanomaterials and anything. I have to go outside and present it. But here, you had an opportunity to learn about nanomaterials and to understand what nanomaterials can impact in the society as well as in professional career. So what I want to know from you is that what do you look after this course? Like, are you look after some applications, or are you looking at the application of the nanomaterials? You have to think on the other side of it. So there is a lot of innovation you can do with nanomaterials, nanoscience, and in terms of biosensors is one of the hot topic, and medical devices is one hot topic is coming up, and the pharma sector there is a lot of opportunity for nanomaterial applications. So think of something innovation, and as always said, we have a T hub. We have a JNT hub here where you can always put up your ideas and get financed and bring your idea into a commercialization. And indeed, I myself also invest on the companies, and we also support startup companies. So if you have a wonderful idea and if you really want to excel as an entrepreneur, okay, we are there to support you. And I'm sure this whole department is there to support you on this. So do not hesitate to contact us, and I wish you all the best. And thank you very much, sir. Thank you, sir, for inviting me. Thank you, Andy. And I wish you all the best. Thank you so much. Thank you.
Now I request all the dignitaries on the dais to present memento to Dr. Vijendra Kumar sir as a token of gratitude.
Excuse me, don't block me.
I request participants to come and collect their certificates. Jangan Shashikala, Robin Joshua, Winston Jovika, Anu K. John, Manu Priya.
Come on, my man. After that, exchange will continue. Come on, good on it. Come on. Come on. Come, please. We'll have a photo with Vijendra, the course coordinator. So you can respond. Please. Gayatri.
Monica, Habibur Rahman, Maliha Khan, Chunduru Ganesh Chandrasekhar, Santosh,
Like this, please.
Navneet Kumar,
Excuse me.
Monisha, Jivantam, Srinivasan, Arya, Mattusa Tamburi, Vinay Kumar, Mohan Kumar, Rajshekhar, Kanishka, Vishali, Praktish Naran, Maitri, Sureka, Gara Tejaswini, Durga, Narayana Divya, Suhana Reddy, Durga Pravina, Amrapudi Ravi Teja, Anusha, Varlakshmi, Rishita Reddy, Swami Raju, Muppasani Roshan Kumar, Sushma, Shivappa, Siri Karusala, Rosie Priya, Akshita, Harshia Kaduri. Ladies and gentlemen, to all the honorable dignitaries on the dais, it's my great honor and privilege to propose vote of thanks on this memorable occasion. I thank Dr. Shilpa Chakra ma'am, Head CLST JNUH for her support and participation. I thank Dr. E.D. Hemalata ma'am, Local Yarn Coordinator, for her contribution. I thank Ramachandra sir for his presence and attention. A special thanks to Professor G. Venkata Narasimha Reddy Garu, Principal JNUH, for his support and encouragement. I extend our sincere gratitude to Professor K. Venkatesh Garu, Beyond Course Coordinator, Registrar JUH.
We will share a Zoom link and one day I will take a class for all. Group is there, those who are interested.
We are deeply grateful to you, sir. Your hard work and commitment made this event happen successfully. On behalf of organization committee, I'm grateful to our foreign guest faculty, Dr. Vijay Kumar sir, for his contribution and insightful lectures. Your efforts have made this a memorable occasion for all of us. I thank today's chief guest, Dr. Aturi Ramababu sir, for being here and making this valedictory function a success. Your presence and support are greatly appreciated. Lastly, I would like to thank all the organizing committee and participants for making it a memorable event. I wish everyone a bright future. Thank you all. Now I all request to come forward and have a photograph with all our dignitaries.
Last group. And one more thing, all the Center for Nanotechnology, teaching, non-teaching, scholars, I thank everyone. Shanika or Harish, please host them Sunday lunch for all. Sunday or Saturday tomorrow, separate lunch.
Please come forward for a photograph.
பேக்ல இருந்து எடுக்க வைக்கிட்டு இதுல இருந்து
All participants are more than 2 lakhs.